So let's shift gears into our course material. So I have been thinking very hard about what it is I want you to be able to do by exam 3, and I've decided I want you to be able to distinguish between different types of reactions. That also means if you need to understand what a precipitation reaction is, you need to understand what dissolving is and what not dissolving is. So we're going to spend a little bit of time on that the next couple days, and then discussing redox reactions. So that's kind of where we're going up until the exam. I've decided that since I've kind of missed the boat on getting you guys up to speed on the lab this week, and it's a 2-week lab, that I don't want to just shift gears, talk about thermo for a day or two, and then come back to this stuff. That I'm happy to help you during office hours. Sam is available, I imagine, to help you with pre-lab. There is a discussion board now within our Blackboard website specifically for lab, so feel free to post there. But I am going to shift gears next week after our exam into gas laws because that is your next lab, and so I want you to be prepared for that.
Yep, come look.
Come look? Why?
Yes.
No?
B and C is switched.
Oh, the letters are switched?
Yeah. I was
Interesting.
Like, what?
Okay, fair enough. So let's use the letters that are on the screen.
Okay.
Because Bria showed me that I actually switched which one is B and which one is C. So I want to have you look at these three and predict which one is going to be the most water soluble. All right, compare with your neighbor. See if you guys chose the same thing.
That's what I think too.
All right. Why? Did you guys justify which one you chose and why? All right, so that's pretty cool. We started out with almost no one having the right answer, and we shifted to a third of the people having the right answer. So turn and talk to people around you and try to figure out why there might be some discrepancy and how we resolve that. Maybe find someone to change their answer around you and see why they might have changed their answer. So ask people around you. If you all have the same answer, find someone around you that doesn't and see which justification is better.
Don't even bother with that.
Okay, so I hear some decent discussion. We have had a shift. We're at 50-50 now. So we're going to talk through some of these things. We're going to come back to this question in a minute, all right? The discussion I want to have is, I think question number 2 on there directs you to do this. I want you to think about how many water molecules will be attracted to heroin, which is the larger opioid-looking molecule. If you notice, all opioids have the same framework. They just have different little changes in the molecule. It might be an OH. There might be an acetate group. Instead of an OH, there might be an OME. There's a lot of different variations on these that are all opioid drugs. So go ahead and try to think about where would water molecules be around this molecule. Take about 30 seconds a minute to try to draw a couple in pencil, and then we're going to come back together and talk about where the water molecules might be around that molecule. I want to see at least one water molecule drawn on everyone's page. So, they're probably on the other side. Does anyone not have a worksheet? Angel, can you grab a couple? Grab one for Ruby as well, please.
Yeah. Some of his dots were at the top.
Try to put it down on paper. Write something down. Write something down.
Wouldn't it be, okay, so an oxygen wouldn't it form with a plus H? Well,
In this series.
What about?
Not very many.
All right.
that's what I'm saying.
So you're looking at the.
So I'm looking at the actual bonds here.
Yeah.
Let's start by talking about what part of the molecule, we're going to have hands raised for this all around the room. I want to hear from lots of different people. What parts of the molecule are we likely to find water around? Kevin.
Oxygen.
Why oxygen?
The hydrogen is attracted to the negative charge that oxygen usually gives. I know. Yeah.
The what charge? I heard someone say it. Partial negative charge on oxygen. So why does oxygen have a partial charge in the locations here and also in water? So I'm going to draw out a water molecule here. Why does water have a partial charge? Matthew?
Because it has two bonds, and that means you have two lone pairs of electrons.
Okay.
And the two lone pairs of electrons are going to have a partial negative.
I see where your logic is going, but that's not why oxygen has a partial negative charge. So if we go back to formal charge, if we're thinking about formal charge, right, those count to the oxygen no matter what. These ones, half of them count towards the oxygen, but that's kind of a lie, right? It's true for formal charge, but where do we find those electrons? Are they always equally distributed?
Closer to oxygen.
Why closer to oxygen?
Because it has more protons, so it attracts electrons.
Not quite. What is the reason those electrons are typically found closer to one atom than the other? Moab?
Oxygen's more electronegative.
Great. So we want to think about electronegativity. It's not just a matter of protons, because then some of the things in the bottom left corner of the periodic table would be very electronegative, and they're not. So it has to do with how close they are to a full shell of electrons, to having 8 electrons, and how small the radius is. So the top right corner is going to be more electronegative, aside from the noble gases. Okay, so we have two polar bonds. We have two polar bonds that are pulling electrons towards the oxygen. That means that oxygen has a little bit more electron density than we originally gave it credit for when we counted formal charge. So it has a little bit of a negative, and we draw that as a delta, meaning a little bit of a negative, which means that each of those hydrogens has a little bit of a plus. All right, that's true in water. Is that true anywhere else in this molecule, in heroin?
Would it not be true for the hydrogens?
Which hydrogens?
The ones all off the carbons.
Okay, so let's draw in one of those and just say, is that true for that hydrogen? Is that hydrogen have a little bit of a positive charge? Just like in water.
When the carbon pulls in the same way, so
How do we determine whether the electrons are going to be equally distributed, pulled one way or the other more?
Didn't you say like a net dipole? Is that-
Okay, so I'm asking if there's a net dipole. That's another way to say it, right? Is there a dipole between carbon and hydrogen?
It's not.
There is a very, very small difference in electronegativity, and we call that nonpolar. If it's nonpolar, there's no dipole, which means those electrons are equally distributed close enough. And so there is no electropositive, it's not more electropositive, and so we don't associate any positive charge, partial positive, with that hydrogen. What about a hydrogen that's down here on this carbon? Would any of those be slightly more positive? There's two hydrogens there, right? Those are both attached to carbon. The electronegativity of carbon and hydrogen are very close. None of those end up being slightly positive. What about, is that true for all the carbons in the molecule? Are all the carbons also no partial positive or partial negative? Talk to your neighbor. Are there any carbons in that molecule that have a partial positive or a partial negative based on what they're bonded to? What'd you guys decide, Gil? What'd you decide?
So it would be more.
Sorry?
So you think that
Carbon always has 4 bonds.
Yeah, because it's. Oh,
True.
that's true. Yeah. Okay, that makes sense. And then, yeah, this one too.
So the question is not necessarily about the symmetry. The first question we always have to ask is, are there any polar bonds? The answer is no, then it's not going to happen. There's none. The question is, are there any polar bonds? Okay. Can I get a hand raise of someone that found where they think that there's a carbon with a little bit of a positive or a little bit of a negative charge? Hand raised. Kiana, are you willing to draw on here where that is? So I'm going to give you green. So maybe circle it or, yeah. And is that carbon going to be a little bit positive or a little bit negative?
A little bit positive.
Nice and loud?
A little bit positive.
A little bit positive. Why? So we're talking about the carbon that's right there. She's saying it's a little bit positive. Why is that? Why is that carbon going to be a little bit positive? Say again? All right, it has less electronegativity than nitrogen. It's not a whole lot less. It's not one of the most polar bonds that we know of. The carbon and nitrogen have a difference in electronegativity. Those electrons that are shared between the carbon and nitrogen are going to be found more frequently towards the nitrogen, which means that nitrogen is a little electronegative, and that carbon is a little bit positive, a partial positive on that. Are there any others in this molecule? Joey, did you find any others that are carbons that are partially positive? Natalie, Lauren, any? Ruby. Circle any carbons you think might be. Keep going. So what are we looking for carbon to be attached to if it's going to be a little bit electropositive? Oxygen and nitrogen, like Kiana pointed out. All right, so we go around the molecule. We look for any carbon that's attached to an oxygen or a nitrogen. We've got almost all of them. Are there any more? Where?
On the side of the nitrogen.
Say again?
On the closer side of the nitrogen.
Okay. Where else? There's 2 more.
On the H3C, both of those carbons need to be circled.
Great. So Ruby found the CH3 attached to the nitrogen. There's also 2 CH3s attached to carbon. Are those going to be polar?
Holy crap. No, they shouldn't be.
Okay, that's it. Done. I did as well. As we talked through it, we realized we screwed up, so it's cool. All right, so Ruby has successfully circled all of the carbons that are slightly positive. Are there any slightly negative parts of this molecule? Say again? Nitrogen. So I'm going to circle those in blue. Anything else? Slightly negative. Has a little bit more electron density close to it than we expected. All of our oxygens, right? Okay, so now we have a map. We have a map of electron density in this molecule. There's more electron density around certain atoms than others. We know that that is also true for water. So can you now go and show where water might be attracted to? What part of water is attracted to it? And where in the molecule? Go ahead and take 30 seconds to draw one water molecule associated with their heroin molecule. And then we're going to talk about what that association looks like.
What was the answer to the first question?
gotten there yet. Doing this kind of, getting back to, we need to do this to answer that question, basically. Did I forget to change the wording of the? So what should that be? What's it referring to? All right. So I'm going to draw something that may very likely happen in this approach. So we're going to draw a water molecule down here. It has a little bit electronegative, a little bit electropositive. And we're going to draw a line between those. So we have electronegative oxygen, a little bit of a negative charge, a little bit of a positive charge on the hydrogen, and we're going to draw a line between those. Why is that wrong? Say again? A line implies a bond, right? A bond is what? Sharing of two electrons. Do we gain electrons by having these things come close to each other? Okay, so the oxygen does have two lone pairs, but that hydrogen that's in water already has a duet. It does not need, and it will not, have extra bonds because it can't exceed its duet. Hydrogen has no more capacity for bonding, so that means that this is an improper drawing. Plus, what we're saying is we're not saying that they're transferring electrons. They're not sharing electrons to become more stable. Remember, that's the reason we make bonds in the first place. So what's a more appropriate way to draw this kind of an interaction? Say again?
Would you take away that line between O and H?
So you're saying we could break this bond? So that becomes a chemical reaction?
Yeah, the one you just did.
Okay, so we remove that line I just did, but then how do we show that there's some sort of interaction between those? We draw a dotted line. So there's a term that you guys are going to spend a lot more time with second semester Gen Chem. That's called like interstate, right? It goes between states. It's intermolecular, between two molecules, forces. So intermolecular forces is the term that describes one molecule, another molecule. There's some attraction between them. We're not forming new bonds. It's not a chemical reaction. It is the biggest misnomer in biology. What do we call this type of interaction in biology? It also exists in DNA.
Hydrogen bonding?
Why is hydrogen bonding a terrible word for that type of interaction? It's not a bond! Some chemist should go tell the biologists that they changed the name of... So, okay, you're going to see the term hydrogen bonding all the time, and this is an example of hydrogen bonding, but it is not bonding. Right? It is an intermolecular force.
Yeah, it's not a bond. Get it right, Paul.
Okay, so here's one. So go ahead and draw as many water molecules as you can around heroin. And then do the same around PCP. Question number 4 should say PCP. Or angel dust.
Otherwise known as solid death.
I think number 4 should say PCP instead of heroin. It's just that I just copy and pasted the question. I forgot to change the name. Say again? All right, so as you're doing this, I want you to click in. I don't think it's a multiple choice question, right? I want you to click in how many water molecules you decide, you figure out, are going to be attracted to heroin. So answer number 2 with your clicker, please, once you figure it out. Yeah, for now we can just refer to them as intermolecular forces. That there's two molecules that are attracted to each other.
They should create another term for that. Or just shorten it until like an actor now, like
Yeah, agreed. It's quite confusing, especially if you're just taking biology and you don't know the chemistry behind it. Then you're like, oh, there's a new bond. All right, so make sure you click in how many waters you think are attracted. So can it attract, can it be associated with those hydrogens?
Like the waters can't pop. I don't know.
All right, I'm going to go ahead and close out and see what you guys responded. All right, so the largest percentage that I can see on the screen is 5 water molecules. So we go back to our drawing here. I've drawn in 1. Let's go ahead and show 1 more. I'm not going to draw as much detail. And remember, these waters are turning and moving. And we have a nitrogen. Right, so anything that's electropositive is going to have the hydrogen of water pointing towards it. Are there any more?
Other one. Oh.
Electronegative?
Did I say electronegative?
You said electropositive.
All right, electronegative will attract a hydrogen from water. Are we done? No. Why not?
You can put carbon.
What about the carbons, Gil? Josh, continue.
You even have it up there in the green, it's slightly positive, so then the oxygens will be attracted to the slightly positive carbons. And nitrogen. Yeah, you have nitrogen. 15.
Okay, so we can do that around the entire molecule. Anywhere we circled in green, the oxygen molecule will turn, and the slightly negative oxygen will be attracted through electrostatic interaction. Think about it as magnets. And so it's kind of an attraction, but there's water moving around all over the place, and so water will be attracted to those sites. So it's really about how many sites are partially positive or partially negative. That's what I want you guys thinking about. Vote?
It doesn't matter then on the bonds they have, right? Because it is electrostatic.
We are not creating bonds. So it has nothing to do. Every single carbon in here has 4 bonds.
Yeah.
That is irrelevant. Aaron? Sorry, I can't hear. Can you speak up a little bit? Can everyone else kind of tone down a little bit? So we're getting into a deeper level of discussion now. So for the point of today's discussion, we don't need to go in that level of detail, but I love where you're going. So what we actually find is that water actually, for every lone pair, can attract a water molecule's hydrogen. So every lone pair is slightly, so going back to what Matthew said, it has to do with the fact that oxygens do have lone pairs, are more electronegative, so those lone pairs end up kind of being the point of contact between the electronegative oxygen.
So would we just say there's 15 sites where water molecules are attracted instead of 15 water molecules?
So this question, the way it's worded, would need to be answered the way that Aaron pointed out. We would need to have 2 water molecules attracted at every oxygen because they have 2 lone pairs. How many water molecules are attracted to nitrogen?
1.
There's only 1 lone pair, so there's only 1 water molecule there. So going back to Caleb's statement, if I had worded this question the way I meant to, it would say how many sites in heroin can interact with water because they're electropositive or electronegative, slightly more than neutral. Oxygen can attract 2 hydrogens from 2 waters, or it could be 1 water that has 2 hydrogens. It could be either way. Joey?
If that's the thing, then how come you have all these waters attracted to the carbons? Because when all those spots are taken up?
What do you mean?
You said that the water molecules molecules, two of them are attracted to oxygen because of the lone pairs. So the carbon, would none of them be attracted to the carbon because they're already bonded 4 times?
So oxygen already has a full octet because each one has a lone pair and 2 bonds. Carbon has a full octet because there are 4 bonds. So intermolecular forces have nothing to do with filling the octet. And that's really a good point to get back to.
No, but you said oxygen has 2 lone pairs, right?
Correct?
The carbons don't have any lone pairs, right?
Correct.
So,
But the attraction, let me get to your point. The attraction is between the electronegative oxygen, the lone pair specifically within that, and the electropositive hydrogen. So this one doesn't have lone pairs. It doesn't have to, right? One of the 2 partners does. So over here where you have an electropositive carbon, that's attracted to the electronegative oxygen. Is that...
I think,
You want to follow up on that, or?
I don't know, I get what you're saying, it's just, the rule doesn't make sense because
Which rule?
you said oxygen attracts 2 of them technically because.
It can. It can. It doesn't have to.
Okay.
Right? So it's water can exist by itself. It
So
does.
Yeah, so we just, never mind, okay.
Aaron?
Wait, why is water attracted to carbon again? Because we said it was non-polar, so it should.
Careful, careful, careful. The element we can't say anything about. We can say if there's a carbon bonded to a carbon or a carbon bonded to a hydrogen, they have a small difference in electronegativity, which means it doesn't have a partial positive or negative charge.
Yeah, so why would it attract to oxygen if it has this?
Because look what it's bonded to. So because it's bonded to an oxygen, these electrons are pulled slightly away from it, which means that carbon is slightly electronegative. So, great point to emphasize. We never say that carbon is polar. We never say that oxygen is polar. It has to do with what it's bonded to. It's about the difference in electronegativity between 2 things that are bonded.
You said that 2 water molecules could be attracted to an oxygen?
Absolutely.
But say we were like trying to figure out how many water molecules were attracted. Would we normally just go with 1 or would we normally go with 2?
So let's zoom out to me letting you know what I expect you to be able to do now. So what I expect you to be able to do on an exam, or if I meet you 2 years down the road, is to say which of these 2 molecules are going to be more attracted to water molecules, which one will have more sites where water will interact. Second semester, we'll spend time saying exactly how many and have different names for the types of interactions that we have. Not all intermolecular forces are called hydrogen bonding. There's a lot of other ones. So we'll dig into that. That's chapter 11. We'll spend a lot of time with that. So for right now, the level of explanation I need you to have is there's a carbon-oxygen bond. There's going to be an electronegative and electropositive site. Water is going to be attracted to the electronegative site from the hydrogen side of water.
And then the oxygen is going to be attracted to the partially positive side.
Absolutely. Yep. Kyle?
Is it still considered a hydrogen bond when it goes from the carbon to the oxygen?
When what goes from
Or
carbon-oxygen?
like on our little dotted line from carbon to oxygen?
Here?
Yes.
No.
Okay.
Hydrogen bond is a technicality where it has to be hydrogen because that is a more delta positive than a carbon would be in that situation. So we got to get moving. One more question.
So if oxygen's, the lone pairs on oxygens attract to the water molecules, I guess I'm just wondering how that would stack up to magnesium sulfate because when you draw it out.
We're getting there. We're getting there. I love it, and we're going to draw it out, and we're going to do exactly what you said. So to answer this question, how many sites would there be? If we ask that question, how many sites did we decide that there would be in heroin? 15. And the molecule is fairly big, so let's keep in mind that ratio of how many sites are polar and have water attracted to them versus how big the molecule is overall. Okay? Let's do the same thing. Can you guys answer this question clearly? This is your question number 3, I think. Let's go ahead and make sure that we're on the same page with this question before we move on. Question number 3. Couple more seconds. All right.
Hold on.
Closing out. Okay. Overwhelmingly, you guys answered almost monolithically that the answer is no, will not form covalent bonds. Okay? I want you thinking about interaction between two molecules, not a chemical reaction where we're forming new bonds. That's great. Let's go to this one. Let's do how many sites instead of... So thanks to Aaron's input, we'll change the wording. How many sites will water be attracted to in heroin? And then go ahead and draw those water molecules around. Oh, sorry, this is not heroin. Angel dust, PCP. Is it not open?
No, sir.
Do we need to click this in? How many? Hold up your fingers. All right, 4 sites. Because we have electronegative nitrogen compared to carbon, so that means each one of these has a dipole pulling in, which means those carbons are all slightly positive, that nitrogen is slightly negative, so we can have 4 possible sites where water can interact. In this case, it actually is the same as a number of water molecules, because nitrogen only has 1 lone pair. All right, so let's think about that. We have 4 water molecules in PCP. We had 15 sites, which can do multiple water molecules. Did I make a mistake?
I'm confused. Did you say nitrogen is slightly positive?
No, I might have, but it was wrong.
Okay.
So is nitrogen electropositive or negative?
Negative.
Negative. Thank you. I drew everything right. I just was thinking about something else when I was talking too fast. Okay? So let's think about that ratio. Based on that ratio of how many waters can associate, which one is going to be more water soluble? Heroin or PCP, and why? You hear a lot of people mumbling heroin. I completely agree. I want you to be able to justify why that is. Okay? So let's go ahead and do... I want you to draw out magnesium sulfate.
Can you put that back up?
No. And I want you should have drawn sulfate a ton of times by now. So go ahead and draw out sulfate, and then think about how many sites water can interact with there. All right, and for the sake of time today, I will put it back up. And because I like Jason.
So which one is the magnesium on one of the oxygens with only 1 bond?
That's a good question.
So why would MG be by itself?
Is it by itself? So what kind of interaction do we have between magnesium and sulfate? It's an ionic bond. And when we have salts, remember we talked about empirical formula versus molecular formula? All salts are described by their empirical formula. So this is the empirical formula for sulfate, but it doesn't exist as just 2 ions. It exists as a repeating pattern of sulfate, magnesium, sulfate, magnesium, sulfate, magnesium, sulfate, magnesium, over and over and over again. So it's kind of difficult to say, is it attached to this oxygen or this oxygen? We're showing the pattern, and on exam 2 I asked you to show the relative stoichiometric amounts of it. But there's going to be another sulfate here with negative charges. And remember, is a negative charge here, 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 or here?
They got resonance structures, so it's all...
So there's an average of half a negative charge on each of these oxygens. There's multiple resonance structures.
I won't miss
So
it.
once again, a reason why we wouldn't put it next to specifically 1 oxygen. There's a lot of reasons for that. Okay, so big picture, how many sites are there that oxygen, maybe let's say it this way, cannot interact with in this compound? Are there any sites that water cannot interact with based on polarity? Polar bond, polar bond, polar bond, polar bond, ion, ion, ion. So what does that mean about its water solubility?
there's lots of places for water to attract to.
So out of our three options, can you justify which one is the most soluble and why? Talk to your neighbor for a sec. Try to come up with a good sentence that describes that, and then I'll ask for you, the group, to report out. Say again? This is exactly what we're going to have on the test. All right, can I have a group that hasn't shared out yet maybe today? Describe which of those three compounds you think might be the most water soluble and justify why. Gail, you raising your hand?
I think it's magnesium sulfate because it has more size compared to the number of bonds it has, so it's going to be almost completely soluble compared to the other ones.
Okay, I would just want to add a little bit of detail to that. Sites of what?
Bonding? Or type of water compared to the size of bonding?
Sites of what with water? Let's be more specific about that.
Attraction.
There are more sites in the compound magnesium sulfate that attract water because they are polar regions, polar bonds, and there is partial positives and partial negatives. The more that ratio increases, the more water soluble a molecule is.
So this one's 1-to-1 though, right? So for every oxygen, every sulfur, every magnesium, there is a site.
True, but it's actually more extreme than that. Because in last class, the end of class, we talked about sodium chloride. In order for that to solubilize, you can't just have a slightly electropositive oxygen make up for a chloride. It doesn't work that way. So you need about 6 water molecules around every ion in order to kind of neutralize it, to mask it. So this is not only 6 sites, 1, 2, 3, 4, 5, 6 sites that water is going to be. We have a +2 charge here. Think about how many water molecules we need to be around that. Think about how many water molecules we need to be around to match those 2 negatives. So it actually is a lot more than just the actual ratio, that the charges that you have will actually increase that much more than a polar site.
Where will the sites around it?
Every single atom.
Because it's 6 and I can see 5.
1, 2, 3, 4, 5, 6.
Okay.
Okay.
The sites to be able to attract more water molecules. So like the oxygen with the double bond, it should attract 2 water molecules.
Yeah, so you're talking about the lone pairs. So these oxygens have 2 lone pairs, these have 3, but remember there's resonance structures. So we say overall, sulfate has a 2- charge and polar bonds, so it attracts way more water molecules than the other compounds. That's where I want us right now. And there was one more point I wanted to make, but I forgot.
So it's the number of sites compared to how many bonds are in the actual...
It's the number of sites, and if we're comparing a partial negative versus a full negative, 2 different molecules, that full negative is going to attract many more water molecules than a partial negative. Yeah, Kevin?
If we know how many sites there are, how do we determine how many water molecules will be attracted?
So the number of water molecules is not something that I'm ever going to ask you, but I want you to use that as rationale on an exam. Sorry. I want you to think about, that's where the framework I want you thinking about. Like, are there just a couple sites where water is attracted? Water is attracted. Or is it the entire thing, right? Or is there 3 parts that are in this part of the molecules? That means that this is going to be more water soluble. That's kind of the experts' framework that we use when we look at molecules to determine how to increase water solubility in the drug. We'll add a polar group onto it. We'll add an OH onto a molecule that might not have an OH in that region. It might be a non-polar region. That's how we get a drug to be more soluble, to make sure that actually if you ingest it, it'll get into your bloodstream. So we think about how sites where water can be attracted to. All right, so the derivative of this that would be an exam question would be which of these is more water soluble and why. You would have to justify that. I wouldn't want you saying there's 17 sites in this one and there's 12 in this one. It would be about the relative ratio of how many waters can be attracted and why. The point I wanted to make is if you have these two ions, this polyatomic ion of sulfate and magnesium 2+, how strong do you think the attraction is between those versus if you have these two? I want you to talk to your neighbor and try to just say which one of these you think is going to have a stronger attraction. Mg to sulfate or Ka plus to Br minus. Talk to your neighbor, try to decide which one of those is going to have a stronger attraction between them and why. All right, can I hear from Stephen or Manu?
You said potassium bromide.
It's going to have a stronger attraction between them?
Yeah.
Why?
Because of the electronegativity between them. Bromide is on the far right, potassium on the far left.
Okay, so I like part of what you're thinking about. I like that you're saying, well, these have a big difference in electronegativity, but that's what made it into K plus and Br minus. So it actually isn't necessarily related to this question. So if we have a metal and a non-metal together, they're going to be very polar bonds to the extent that we actually call them ionic bonds. So if we have these two ions versus these two ions, what can we say about how difficult it would be to pull them apart for each of those two? Aaron?
Wouldn't it be the same as if like, you found, I don't know, for instance, oxygen in nature, so they rely really strongly on each other and make them those full covalent bonds, so they're harder to break. The strong difference in between the two charges mean that they rely more strongly on each other, magnesium sulfate versus potassium chloride. So
Okay.
it'd be harder to break them apart.
I see where you're going, and a lot of the parallels apply. We got to be a little bit careful when we compare covalent and ionic bonds, though, because they're not essentially sharing electrons with each other to reach their stability, right? They've already transferred the electrons. But where you're getting at is that there's a very strong attraction between them because they have opposite charges. So if we were to guess, let's do a hand raise. Do you think potassium bromide is going to have a stronger attraction between them? Do you think the magnesium and sulfate are going to? Okay. So the logic behind that, what's the logic? Taylor, you want to give it a try? Josh?
Magnesium and sulfate are further up the scale of electronegativity
So careful, careful, Josh. We're not talking about sulfur or oxygen. So once we have a molecule, we can't just use its position on the periodic table. Jackson?
Well, magnesium and sulfate both have 2+ charges, so you know they're going to attract each other twice as much. You know, by logic.
Right. I think you guys are way overthinking this.
Yeah.
Right?
Yeah.
So there's Diana?
More attraction sites?
So there's more attraction sites in sulfate, and even I think the overpowering is going to be the overall charge of each of them, kind of combining what you guys said. So a 2+ and a 2- charge, if you're trying to pull those apart, think about magnets. You have them that are twice as strong as each other, it's going to be much more difficult to pull those apart. So when we put compounds in water, the question is how likely is it the water can overcome the attraction between two things? If you look at your solubility rules, right, on the exam I'm going to give you that table with the gray boxes and the white boxes. I want you to start noticing some trends on there about which ones are more attracted to each other, and hence if you put them in water are not as likely to be dissolved. Right? Dissolving means that those ions are now surrounded by water instead of being surrounded by the other ions themselves. That water can actually replace that charge. So out of these two, potassium bromide is going to be much more soluble because it's much easier for water molecules to surround potassium and kind of shield that positive charge, and same with the bromide pointing the hydrogens in. These are going to be a bit more difficult to solubilize, and I can't remember on the solubility chart if this is actually a soluble compound or not.
I think it is.
Okay? And that might be because these negative charges are actually spread out a little bit, and it's not a 2-. I bet you if we had magnesium oxide,
NGO,
that would not be water soluble, because those are point charges, 2 plus 2-. They're going to be harder to pull apart and get water in there to displace those from each other.
and in fact MgO is magnesium oxide is not soluble basically at all.
Sounds right. So what I want to do, there's a lot of stuff I wanted to do today. Let's look at this question in our last couple minutes. On the back side, well, maybe before we dive into this, I want you guys to try to work out question 11 before class on Friday. And then the questions above that, I think you guys can do most of the questions leading up to question 13 on your own. So let's have those. We'll touch base with those on Friday. I want you to look specifically at question 13 right now. So you guys know the types of reactions that we have. I think it's listed right above the question, right? There's 3 types of reactions there. Those are the 3 that for most of chemistry we're going to choose from. All right. So have you gotten a chance to look at some of the questions, some of the reactions? Let's bring it back together. We have 2 minutes left in class, 1 minute. I want to make sure that we're all on the same page for these, and then for Friday's class, the pre-class quiz involves redox and starting to get you thinking about oxidation numbers, and we're going to spend a lot of time with that on Friday. An acid-base reaction. Let's make sure we're all on the same page about what that is. You guys have been doing this in lab now for 3 weeks? 2 weeks? It's when you transfer an H plus from one molecule to the other. Do you see any in that set that transfer an H plus from one molecule to the other? All right. So the first one, you see an H plus going from nitrate to ammonia. Right? There's a transfer of an H plus. And there's an example here as well where you have an H plus being transferred from HCl to OH minus. Precipitation reaction. You guys have done these in lab as well. You start with things that are dissolved. You end up with, like magnesium oxide we were talking about. If magnesium and oxide were floating around in water together, if they run into each other, they're going to have a really strong attraction because they're 2 plus and 2 minus. More strong than water's interaction, and they're going to fall out of solution. Right, so we always have aqueous that we start with. We end up with, once these are all dissolved, we're going to have some pairing of that are going to have a stronger interaction to the other ion, and they're going to form a solid as a product. And then redox reactions. What's transferred in a redox reaction?
Electrons.
Electrons. All right, so we're going to have to think about what does it look like to transfer electrons. So here's an example. We start with zinc. It has all of its valence electrons. And then the product, it's missing 2 of them. Copper started out missing 2 of its valence electrons, a +2 charge. It ends up not. So we're going to have you in your pre-class quiz, you're going to have to learn how to determine the oxidation number, which relates to valence electrons, but is a different way of counting than formal charge. And you guys are going to get questions like this on the exam. We're going to have to go through and determine what type of reaction each of these is. And you're also going to have to determine oxidation numbers. So the homework you're doing for Friday is we're going to use, make absolutely sure before you come to class, do your pre-class quiz, and really try to do questions 6, 7, and what is the other one that has you?
Can you go back one slide?
6, 7, and 11. Those are things you should be able to do, and we're going to make sure to practice that together.
Thank you for my credit.
So, right in Manu. Manu.
Oh, yeah, I buy these.